Video is going to be about Lorentz transformations. Now pay attention, this gets a little bit tricky, especially with the example, but it's pretty cool stuff. So what we need is actually two reference frames right here, and a reference frame is just a coordinate system. We're going to call one reference frame S and another reference frame S prime. And S prime is going to be moving at a speed v relative to S. Of course, we could have S moving relative to v and it would all work out since this is all relativity. V has to be a constant speed, and this makes them inertial reference frames. And what we're going to do is we're going to look at a couple of events that happen, or an event that happens. So an event is just something that happens somewhere at a particular time. So let's say, boom, right there, there's an event, a flash of light or an explosion or something happens, an event. And I want to keep track of where and when the event happens in S prime compared to where and when the event happens in S. Because what we know is that where and when are both relative concepts. So someone in reference frame S is going to measure those coordinates and times differently than someone in S prime. What we're going to need to do is figure out where and when did S happen. So let's get some coordinates down for this. What I mean is that if we're in reference frame S, we want to figure out where it happened. So where it happened, we're going to need a coordinate x, we're going to need a coordinate y, we're going to need a coordinate z to figure out where that thing is. And then when it happened, we're going to need a coordinate t. Right? For S prime, we're going to need also three coordinates, which we're going to call x prime, y prime, and z prime. And then it happened at a time t prime. So these are not necessarily going to be the same. Now it's going to turn out that the y and the z are not going to matter so much. But let's back up and not do relativistic transformations yet. Let's go back and talk about what they call Galilean transformations from Galileo. And what Galileo said, which makes a lot of sense, is that, well, time shouldn't be a relative concept. So first of all, t should equal t prime. Anytime, if you mark the time of an event in S and in S prime, they should basically be the same. And as far as the coordinate systems go, the y coordinates are all going to be the same, and the z coordinates, which I can't draw on here, are all going to be the same. And how do I relate the x coordinates together? Well, if I want to figure out, I should have written this differently. I should have said t prime equals t, because what I really want to do is say, how does x prime relate to x? Well, what we can do is we can say, here's where x prime is, right there. That's where this event happened in this coordinate system. And where did it happen in this coordinate system is going to be x, which is going to be all the way over there. So that's x, that whole distance there. And if I want to relate x and x prime together, then I just have to figure out, well, how far is that distance right there, right? And if I know how fast this thing is going, and I know how much time it did that for, then this distance, this black line right here, has a distance of speed times time, right? That's how much that is. The distance right there, how fast this is going, and then it's just speed times time. Distance equals speed times time. So what I can do for what they call this Galilean transformation is I can say x prime is going to be this x coordinate all the way up there minus v times t. And that's really simple. I mean, all it really says is that this event happened further away in x, in the s reference frame, than in s prime reference frame. But this is actually not true. Not true for high speeds, right? What I mean by high speeds is something that's appreciable percentage of the speed of light. If this is 20 miles an hour or even 1,000 or 1,000,000 miles an hour, that's not going to really work. But if we're talking hundreds of millions of miles an hour, then this system is not going to work. These Galilean transformations aren't going to work. So I'm going to write for you what the Lorentz transformations are, and you're just going to have to take my word for it that they work. And to tell you the truth, I don't know that I could figure this out on my own at this point. At some point somebody told me how this works and why it works, but just got to take my word for it and take the book's word for it that this is how it goes. So it's tricky, but it looks like this. If I want to figure out the relationship between x prime and x, that is, where did this event happen in this reference frame compared to this reference frame, I have to do this. X prime is good old gamma times x minus vt. Y and z are the same. Doesn't really matter, y and z, because they're perpendicular to the direction of motion. And then as far as t goes, t prime is gamma times t minus v times x divided by c squared. So that's how you go from x, where did the event happen in one reference frame compared to the other, and when did the event happen in one reference frame compared to the other. And I can reverse these around a little bit. So if I want to find x in terms of x prime, I'll write it down here. It's just x equals gamma times x prime minus plus v times t. Just do the algebra, it works out. And then t is gamma times t prime plus v x prime over c squared. So this is how you get back and forth between t and t prime and x prime. That is, where and when did the event happen in one reference frame versus the other reference frame. It also turns out that sometimes we want to actually have two events that happen. So let's say I have an event here and I have another event right there. So maybe I could call that event B and I could call this one event A. So now sometimes I'm more worried about, well, what's the displacement between these two things? How far apart were they? So what that means is I can actually have a delta x and a delta x prime. How far apart were these two events? And I can also talk about how far apart were they in time, which means delta t and delta t prime. Right? How far apart were they in distance and how far apart were they in time? This one happened and then this one happened. They were 5 seconds apart and 300 meters apart or something like that. Right? And these are actually pretty easy to figure out as well, just plugging in the deltas. So I can change this one around to say, well, actually, let's do it over here. Just more space. What I have to do now, delta x is gamma times delta x prime minus v times delta t prime. Whoop, barely made that in. And then delta t is gamma times delta t prime minus, oops, this should be pluses, plus v delta x prime over c squared, right? All I did is I substituted in deltas for all these things right here. Okay, so let's do an example. I think this will really help us. So just remember these. I'm going to refer back to them. So put those away. We'll bring them back in a minute. And let's do an example. Let's figure out where I did my example. Okay, so here we go. We're going to have Bob and Sally. We're going to have Bob is going to be an S, and Sally is going to be an S prime. And they're moving relative to each other. So let's make it faster this time. Let's say they're moving at 0.9 c relative to each other. So Bob is moving relative to Sally. Sally's moving relative to Bob. It doesn't really matter which ones we consider at rest and which one we consider moving, right? Because it's relativity. Before we move on, we're going to need gamma as a number. So let's just sort of quickly figure out what gamma is. Gamma is 1 over the square root of 1 minus v squared over c squared. And I did the calculations for this. I think we did this in class as well. It turns out that gamma is 2.3. So that's just for reference for this. Now let's talk about Bob. Well, Bob and Sally's perspective. But Bob, let's say he sees two events. All right, and he's going to measure how far apart they were in space, and he's going to measure how far apart they are in time. Right? Just to pick out some numbers, let's say he saw two events and they were 600 meters apart in distance and 2 microseconds apart in time. It was one lightning bolt and then another lightning bolt, or one person said hello and then another person responded with hello 2 microseconds later, something like that, whatever they are. What I want to figure out is, what did Sally see? So I want to find delta x prime and delta t prime. So according to Sally, how far apart were the events in distance and how far apart were they in space? Right, we just have to go back to these equations. So I want to find delta x prime is gamma times delta x minus v times delta t. All right, let's find that one. We'll just start plugging in some numbers. We have gamma, that's 2.3 times delta x is 600 meters minus, now the speed v is 0.9 times 3 times 10 to the 8th meters per second. and delta t was 2 microseconds. That's 2 times 10 to the minus 6 seconds. Just note here that the units are going to work out. So this is going to be meters, this is going to be meters, and delta x prime will end up in meters as well. So do this math out on your calculator, and you end up as, this is 138 meters. So Sally disagrees. Sally thinks that they actually were closer than what Bob sees them. Right? So if Bob measures the two events as 600 meters apart, then Sally's going to measure them as 138 meters apart. Right? Who's right? They both have an equally valid perspective. Now the time thing I find actually more interesting. Delta t prime is gamma times delta t minus v delta x over c squared. Be really careful when you're doing this that when you see this delta x here, you're doing delta x, not delta x prime. Right? Just plugging in numbers here, we know that gamma is 2.3, delta t is 2 times 10 to the minus 6 seconds, minus v again, 0.9 times 3 times 10 to the 8th, times delta x, which is 600 meters, 600, I dropped my units, sorry about that, divided by c squared, 3 times 10 to the 8th squared. Do all this out on your calculator, and you end up with delta t prime is 0.46 microseconds. So that's actually really interesting, because she sees the events as happening closer together in time than what Bob did. That's just how it goes. And if we fiddled around with these numbers right, we could actually maybe get, not for this one, but maybe I choose a different value for v and for x and for this. This could actually work out so that delta t prime was 0, which means that Sally saw them as simultaneous, even if Bob didn't see them as simultaneous. Even stranger, I could get a delta t that was negative. Let's say I got it as negative, I don't know, 1 microsecond. What that means is that Sally would actually see the events happening in reverse order to what Bob did. If Bob saw event A happen and then event B, Sally would see event B happen and then event A. And neither one of them is actually right, or neither one of them has the correct association. So we get into some interesting things with causality, right? So if I have event A, if it causes event B, then I always have to have my observers agree that event A caused event B. But if I just have random events like something happened here and then something happened there, these two events might be in reverse order for somebody else. Somebody might see them as happening simultaneously. Someone sees A happen first and then B. So I think that the time aspect is sort of interesting for this. But it all comes back from these Lorentz transformations, these guys right here. And once again, you're just going to have to take my word and the book's word that they actually work. This is how it goes. And that this equation is wrong from Galileo, that for high speeds, you can't just simply agree that the time is the same and that the distance is just based upon the speed. There's a couple examples in the book that you should take a look at, and also some homework problems as well.